What I'm going to do is I'm going to talk about the various subsystems of a typical satellite. Okay, you've looked at it to help you with designing a satellite. You need to have some basic understanding of the various subsystems. Okay, now it's going to be a little bit challenging in that you don't have all the know-how, okay? Because as I told you, satellite engineering is multidisciplinary, right? And right now you don't have that multidisciplinary education, so to say. We try to make sense of it as an engineer, okay? Typically, you can start with these are the various subsystems of a satellite or guys, pay attention. Okay. So the first is attitude and orbit determination and control system. Okay. I'm introducing this first because this is really what you have to study in detail. Okay. Attitude and orbit determination and control system. Okay. Second is telemetry, tracking, and command. Okay. And then you have the command and data handling system. Okay. So all these have acronyms. Typically, this is called this is a special case, okay, orbit. Without the orbit, it is called ADCS, and with the orbit, it is called AOCS, okay? Attitude and Orbit Control System. All right. This is called the TTMC. This is called the CDH. Then you have the electrical power system, okay, or the EPS. What I'm going to do is I'm going to add this. But we are going to discuss this in the context of this, okay? And of course, you will also have, it's not quite a subsystem, but when you study this part, you're going to study the space and ground segments. Okay? So this is the communication segment, communication subsystem. When you study this, you're going to study the space and ground part of the
Why did you put a star? Why did you put a star next to the propulsion system?
What we'll do is see, propulsion system, here is how, we'll give you a little bit of overview. Propulsion system will facilitate attitude control or orbit control. You got it? It is a physical system which will facilitate a function. You got it? Does that make sense? But it is studied separately. Okay. Here this is SNP, structure and thermal. All these have functions. Okay. This one will facilitate one or more of these functions here. Okay. Now we'll talk in depth about attitude, not a whole lot in depth, but relatively in depth about attitude, determination and control system. Okay. To talk about this,
Attitude and altitude, right?
yes. So this is a very important word, and when you go out of your aerospace realm, people are going to ask this question to you, or they're going to try and correct you as well sometimes, saying it's altitude. It's not altitude, it's attitude. Attitude is another word for orientation. Okay. For spacecraft, attitude is much more critical, because we'll demonstrate in STK altitude. How do you control altitude? What is altitude control in spacecraft? Huh? Altitude control. What is altitude control in terms of space? Huh?
I don't know, plane temperature, distance, or your height above the Earth.
Right. So that is this orbit control. Okay. So orbit control is similar to altitude control for a spacecraft. Does that make sense? Because orbit defines the altitude, right?
On number 2 and 3. Why is command included on both of those?
So here, telemetry is that which comes down.
Right.
This is all data. Okay. This is telecommand. Okay. So there is data going up to a satellite
Right.
and data coming down from the satellite. This is data coming down. This is data going up. This is the system required to make that possible. Yeah. Right. So this is the onboard computer and the onboard software. Alright? We have to first figure out what data, and then we have to design a system to handle that data. This is all data. Telemetry is that which goes up, or telemetry is that which comes down. Command or telecommand is that which goes up. Okay, does that make sense? Data going up and down. Tracking is what? Tracking is essentially figuring out where your satellite is. Even before you do this, you do this. Okay, we'll talk about that. So when you're trying to determine, or when you're trying to design this system, and I want you to try and design this system for the satellite mission out of what we're doing. Okay, the space ground satellite, the state of Alabama satellite. Okay, try and design this system. I'll give you the specifications, or I'll give you the requirements. You can try and do that. Okay. First, we'll discuss control modes. Try to understand this. Put yourself, whenever we are discussing about satellite, put yourself in the orbit. Alright? You have to start imagining yourself in the orbit, and the way you're going to do that or realize that is by doing STK simulations. When you do enough STK simulations or orbit simulations on any software, you will get that idea. You will try to start going to orbit. Okay. So the first is orbit insertion. This is from a textbook. We'll talk about this. The second is acquisition. Third is normal or form station. Contingency. Or C. And fifth would be. These are the control modes of a satellite. And when you talk about attitude, determination, and control, you have to understand what are the general control modes which a satellite will go through when it is in space, when it is orbiting. Okay. So orbit insertion. All right. What do you understand by orbit insertion? So it is. When the launch vehicle goes up like this, it will insert something, right? So how is here a launch vehicle or a rocket will do that? A satellite itself may insert itself into another orbit. Does that make sense? Because it may go from one orbit to another. Alright? That is one it is in a control mode during that point. You understand? Okay. Acquisition. What do you mean by acquisition?
Receiving.
Acquisition is understanding what its
Capable.
what its attitude is, or what its orientation is. You see, let's say think about somebody inserting you into the orbit, right? What is the first thing you are going to do once you are inserted into an orbit? You're going to try and stabilize, but also at the same time you're going to try to figure out where you are pointed, right? You'll be doing this. That is not under your control, not a whole lot, okay? But you need to figure out where you're oriented. You understand? Even before you stabilize, you need to figure out where you're oriented. Whether you're doing a lot of that or you're pointed somewhere, you need to figure out where you're oriented. Okay? Acquisition is essentially figuring out what is your orientation or what is your attitude. Attitude determination is acquisition. Okay? What is this? So this is typically your mission. Mission time. Okay. Now, are you doing anything related to the mission here?
Yeah.
Think about what you're doing. Okay, you are required to do a particular task. Okay? Let's say you're required to take the picture of Earth, or when you get inserted, are you really taking a picture of Earth?
No.
You get it? You're not taking a picture of Earth here. Here, you are getting into a mode. You are inserted. Okay, and then this is a mode in which you're either preparing to get out of the launch vehicle or go from one orbit to another. That is the insertion. Okay, you're in that mode. All right. Think about this. If you're traveling on a bus, have you run and caught a bus or train or something like that?
Yeah.
Carlos? Okay. So we do that, right? So when you prepare for that, you understand? This is something like that. You're preparing to get out of the vehicle. You have to be in a particular orientation or a control mode in this. Okay. Once you do that, what do you do inside the bus? You try to figure out where you are. Okay, this is that part. Here is the actual traveling. You start reading or you take by or this thing and do what you. This is the mission time. If you're looking at something like a GPS satellite, okay. So what happens to a GPS satellite, or what happens to the station, for example? The station was built piece by piece, so it's difficult to imagine this. But GPS satellite, you think the GPS satellite were inserted exactly in the orbit they were designed for? They were put in a. Do you think a rocket will go all the way to a geosynchronous orbit? How far will a rocket go?
Just past Earth's atmosphere. Just past Earth's atmosphere. Earth's atmosphere.
Why is a rocket required?
So it escapes atmosphere. So as soon as it hits
Huh?
after it leaves vacuum, it's no longer functional?
After it leaves vacuum?
I mean, once it enters vacuum.
Okay. So a rocket is merely required to overcome the atmospheric resistance. Once a majority of the atmosphere is over, you don't need a rocket. You understand? So if you're going to insert a GPS satellite, where is a GPS satellite? What is the duration? What is the orbital period of a GPS satellite? Do you know, Vic?
You said what?
GPS satellite, what is the orbital period? Huh?
Like how long it takes?
How long is it? It would depend on the orbit. It depends on the orbit.
Doesn't it? That's I can't really answer that.
It's in a circular orbit, right? It's in a circular orbit. Well, GPS satellites are in circle.
It's 24 hours. All GPS satellites are geosynchronous satellites.
They all take 24 hours?
Yeah.
They didn't tell me that.
All, see, how many GPS satellites are there?
A lot.
Huh?
A lot. I'm just guessing.
At any given point of time, you need how many? 3 or 4, right? At least. But there's a whole constellation of GPS satellites. The relative position of GPS satellites does not change. Okay, they have to be put in a 24-hour orbit. You got it? Where the relative position does not change. So if you want to put it in a 24-hour orbit, you have to go thousands of miles. Okay. For example, if you want dish TV, dish TV is in a really far off distance because the relative position cannot change. What happens is, if it's in a low altitude orbit, what happens? It is going to do that. You'll get signal, you'll lose signal. You'll get signal, you lose signal. Okay, you cannot do that. So it has to be really high up. You don't want to send a rocket so high up. It's not required. It's a waste of money, fuel, everything. You don't want that heavy. What does a rocket carry?
Fuel.
Payload and fuel. Okay. So you need most of the fuel required is for getting out of the atmosphere. Once it gets out of the atmosphere, what does it do? Yeah. Only so if you have 3 or 4 stages of a rocket, the first boosters come off, right? They fall into the sea. Okay. The first stage, second stage, third stage come off. Only the 4th stage is probably the final stage of the rocket. Is the only stage which will remain in orbit, which will cause debris. Okay. All the other stages are jettisoned. So they come down, they fall down, and they become structures for fish.
Reefs. Reef.
Reefs are natural.
But you can plant an artificial reef. Or, yeah, an artificial. It's a reef. It becomes a reef.
What is?
How does a satellite move between orbits though?
Yes, so that's what we do. Satellite has its own small tanks, okay, small propulsion system. So you insert it into that, and then from there on, it'll put itself there. Okay, and that is that orbit insertion. You got it? So it will be in an orbit insertion mode. Now, where is a GPS satellite supposed to point? Always towards the Earth, right? It is a directional thing, it has to point towards the Earth. It cannot point the other way. You understand? Before it points towards the Earth, it needs to know where it is pointing, right? It cannot suddenly start pointing not knowing where it is. So that is the acquisition. And then once it figures out where it is, it will point and then it will stay pointed. This is the mission, right? This is the mission of a GPS satellite. If you look at the normal on-station operation, what kind of a satellite is a GPS satellite? I'm going to ask this on the test, okay? It's a nadir pointing satellite. What's a nadir pointing satellite?
Okay, go ahead. Alright, I just got it.
You have to understand these two terms. In the satellite world. What is nadir pointing? When you're up in space and you're pointing to the satellite, that's nadir pointing. You got it?
Is that when you have to say something important?
You're pointing towards the earth.
Oh,
So the camera, what is, how do you define this? It is perpendicular to the orbit tangent. Does that make sense? What is zenith?
It's the highest altitude. Is that?
It's not.
pointing away.
Zenith is not pointing, yeah, it is pointing away, but zenith is if you were to look up straight, you would lay flat. So the perpendicular to the earth tangent is zenith. That seeing directly up like this. You cannot see like this. If you see like this, what do you see? You don't see horizon. You literally or virtually you lie flat on ground. Okay. If you lie flat on ground, what will your eyesight be? Perpendicular to that tangent, right? If you lie flat on ground, that will be the tangent to the ground, correct? And if your eyesight is perpendicular to that, then that is the zenith direction.
So native.
Nadir is coming down and zenith is going up. Okay. All Earth observing satellite are needle pointing satellite. You get it? All ground stations are zenith pointing. Although they are not necessarily zenith pointing, but you can say they do that. Okay, they change. But you can, if you have a ground station really up, if you have a space observatory or something like that, they'll be zenith pointing. Okay. What is this? Contingency or safe?
Just in case anything happens.
Right. So this is the mode in which something may happen. Alright. That's when you need. For example, think about when you put a GPS satellite in contingency and safe. You don't want to put it in a contingency and safe, but when will you put it? Or when would you think about putting a satellite in contingency and safe mode? When the power on that satellite is exhausted. Okay. So for all these modes, for example, this, it is using some sensors and actuators, right? So if you don't want to use those actuators or sensors, you put it in this mode. What are some of the special modes?
Be like a special part of the mission.
It could be a special part of a mission. Okay, for example, if your mission is, so this is a GPS mission is a continuous mission, right? Your mission need not be continuous, correct? In that case, think about a special mode. Special mode could be
And added to the satellite, like something extra for the satellite that separates it from another satellite.
So if you like turn the camera to it?
Camera would be part of this, right?
Okay.
So for example, if you had solar cells, okay, and you wanted to point the solar cells towards sun, okay. If your satellite configuration is not such that when the payload is pointing to Earth, the solar cells are pointing to sun, that's when you would want to use something like that. Okay. Or if you want to have communication, if you are trying to if you have these dish antennas, right? You sometimes have dish antennas on satellites as well. Where do you point them? To Earth, right? You cannot point them anywhere. Now, if your satellite, if you're limited in your configuration or in your design, not to have, so for example, if you design a satellite, typically what you'll do is, you design a satellite, okay? So this is Earth, alright? This is Earth. Where is Sun? You got it? How will you design your solar cells? You will design your solar cell such that, if this is the solar cell, you will design it such that they are always pointing to the Sun. Your communication will be designed such that it is always pointing to Earth. But if you are limited in your design, you cannot do that. If your solar cells are here, right, and if the communication system is also here, if the solar cells and the communication system are on the same side, you need to do this to generate power, right? Once you have generated power, you need to do this to communicate. You understand? What will that require? That will require all these modes will require attitude determination. Alright? So you need to figure out, as aerospace engineers, this is something you need to figure out. Alright? It's very, very critical, very, very crucial that you understand this aspect. All these, so this could be, most satellites are, or many of the satellites are communication satellites. Communication is a big aspect of why we need, what are the different types of satellite applications? Communication satellites, right? What are the satellites? Think about what kind of other uses satellites are used for. Research.
Collecting data.
That's what research is.
Huh?
Research is collecting data.
Taking pictures.
I guess that's what.
Specific.
What's
Communication satellites, right? Communication satellites, where do they point? Always towards Earth, unless it is.
Would it if it was communicating with another satellite?
Yes, unless it is inter-satellite communication or interplanetary communication. You will always point towards Earth. Okay. There are Earth observation satellites. Earth observation satellites for what? Why do you use Earth observation satellites?
Figure out the weather.
Weather, right? Weather satellite. That's what I wanted you guys to say. Weather. Weather is a big application of satellites. Taking pictures is not a big. Of course, weather satellites do that, right? They take pictures, but weather is a big application. So when you look at weather satellites, where are they pointing? Towards Earth, right?
Constantly.
Huh?
Constantly.
Constantly, yes. What other satellites? Research. Name one research satellite. Hubble. Where is it pointing?
Away from Earth.
Away from Earth. So you can generally categorize as Earth observation and
Planetary observation? Or space?
space observation. Okay, Earth observation and space observation. There are two. So Earth observations are weather satellites, communication satellites.
GPS.
Space observation, GPS satellites. Space observation satellites are largely research satellites. Okay, they are pointing there.
Don't they have telescopes?
Huh?
Don't some of them have telescopes?
On ground.
Yeah.
What is the limitation?
The limitation on a telescope on the ground. One is range. Range, you can't.
You can
Well,
point.
actually, now there are telescopes in Hawaii.
There is attenuation of the signal. Okay, once it enters atmosphere, the signal gets corrupted. You do get. There are very big ground-based telescopes, but what you can get in space is nothing. You cannot. Even with a small satellite which can fit in your palm, you can get a really nice space observation satellite compared. You have a telescope which is pointing, the light gets diffracted, right, when it enters the atmosphere. So it is very difficult to process that light and get some clean data out of it. But if you put something out of atmosphere, you really get some really incredible things. Now, I want you to think about these things, okay? Do a little bit of reading of these. You can read about these in any of the reference books. The reference book is pointed out in the syllabus. I'll upload the syllabus today. For next class, what we'll do is, so these are the control modes of a satellite. Okay? We'll talk about what are the different methods of controlling, or satellites themselves can be classified into different categories based on the attitude determination control system. For example, I'll give you one example. You know what a gravity gradient satellite is?
Gravity gradient.
What is a gravity gradient satellite? Also, what will it become eventually? You know what a gravity gradient is?
Direction.
You know these big clocks with pendulum? So what happens to the pendulum eventually if it's not powered? Huh?
The clock stops working.
The pendulum stops moving.
The clock stops working.
You guys have to talk in terms of aerospace engineering. You cannot say his clock stops moving. It's English. You cannot talk English. Huh?
It drops out of orbit.
Loses momentum.
And the clock stopped turning.
It aligns with the gravitational force. You get it? You put it in any direction. It'll always align with the gravitational force or the gravitational vector. You can do the same thing to a satellite. You have the satellite, right? A square satellite, let's say. And you attach a big load at the end with a big boom. It'll do this and it'll align with Earth's gravitational thing. What kind of satellite would that become?
Wait, say that again.
What kind of satellite would that become eventually? Huh? Opposite.
Oh, not
Nadir, right? It will become a nadir pointing satellite. You understand? It will do this. If you have this, okay, let's say this is your satellite, okay? You have this gravity, this thing, the pendulum attached. You have a big pendulum attached here, alright? It will do this and it will align with Earth's this thing and it will do that. It will always be aligned with Earth's. You get it? That is the nadir pointing satellite. You understand?
Yeah.
So that kind of if you have that kind of a satellite, what is the application of such a satellite? This is the last question. Give me one application of such a satellite. Or what would it also become? We just discussed it. GPS would be such a satellite. It would become an Earth observation satellite. You got it? It is an ideal case for communication GPS Earth observation satellite. You got it?